Well, hi everybody. As Jack said, my name is Cody Hatfield. I'm a PhD student, and I like playing around with math and artificial intelligence and stuff like that. And I also really like art. So a lot of my little side projects that I like to do outside of my professional research tends to be a bit more artistic in its focus, just because it's fun and expressive. So today I will be giving y'all a lecture about this cool little technique that I've been playing around with lately, and as which is very related to the title of this lecture, which is image processing with physics. We're basically going to be simulating a sort of quasi-Newtonian physics system and put a bunch of particles in that system, and we're going to get some pretty cool results, as you can see by the clock tower image on the left, which was generated with this process. This presentation is brought to you by the Katin Kollective. It's a programmers collective based out of DFW. We basically just explore fun, new, interesting, and artistic applications of advanced scientific ideas. So a basic outline is I will be going over the requirements you'll need in order to do this kind of stuff. I'll be talking about some prerequisite knowledge that we're going to need, such as vectors, surfaces, and like the topology of the shapes we'll be interacting with. How we can convert images into this surface and its topology. We'll be going over the brush particles that we will be simulating inside of this this physics world. I will also be describing in a little bit of detail the cycle or the simulation cycle that we undergo, as well as how this results in some interesting descent and emergent behaviors, as well as how we can guide this emergence. And I will be ending this lecture with a conclusion and a question and answer session. So some basic requirements. I will be posting the source code for what I am. Here, do I still have access? There's chat. I'll be posting the source code in the chat for anyone who wants to download it and kind of play around with it while I'm giving the lecture. Or you can just, for those of you who are watching the recording, you can just go to the URL that's on the screen. This procedure that I'm going to be using relies on NumPy and OpenCV2. I programmed it using Python 3.7. I'm pretty sure other versions should work. I just wanted to let you know the version I use just in case there were issues. Without any further ado, let's get started. So as I said, we'll need to be going over some sort of prerequisite knowledge as well as some data structures that I created to help with this image processing procedure, which are the vectors that allow us to define the fundamental forces of this world, some surfaces, which is sort of like the world or the environment that we're operating in, as well as a brief discussion on topology, which is sort of like the structure of the surfaces and how we are moving across them. Now, our vectors, I went ahead and I implemented them as a simple class, but you really should think about them philosophically as a primitive. I took a lot of inspiration from the Unity physics engine in this regards, because they treat vectors as primitives as well. What this means is that the vector is more about storing and retrieving, a certain set of information. And there are some methods defined in the vector because it is a class. But it's very simple stuff like adding two vectors together, calculating the magnitude of a vector, getting a unit representation of that vector. So again, when you're looking at the code, try to philosophically view these vectors as primitives and not classes. They are limited to 2 dimensions, just because trying to go into higher dimensions was frivolous and unnecessary. Now, our surfaces are as I said, they're the environment or the world that we're sort of operating inside of. I implemented them as a data structure, which essentially just manages a 2-dimensional NumPy array. And this NumPy array is loaded with some base image, and I'll be explaining how that process works in a few slides. Each point in this array corresponds to an XY position of a vertex of our surface, and the Z value gives us the value of the array at that position gives us the z position of the vertex. So our images basically can be interpreted as these three-dimensional surfaces. So because this is a NumPy array and we're operating on pixel values, the xy positions are discrete integers, whereas, however, the z position are continuous, as I normalized the intensity values of the pixels between 0 and 1. They just make the math and defining the constants a little bit easier if you do that. The surfaces were also built with a few really useful operations so that we can analyze and work within this surface, such as finding the sample gradient. You might also call that like the rate of change in an immediate area surrounding a pixel, as well as determining local minimums, calculating some forces, and transformations that can occur inside of these surfaces. Now, we need to have a brief aside about topology. I'll try and keep it short because topology means a lot of different. It's a very large field that means a lot of different things to a lot of different people. For our purposes here, you can kind of think of topology as the structure of the surface that we're operating upon, and how we can sort of move and interact across this structure. So, while our surfaces are technically three-dimensional, what we're going to do is we're going to treat them as a mapping from a two-dimensional space into a one-dimensional space. So a function from a xy position to a z position, essentially. Now, what this does is it allows us to sort of interpret this function as us moving through two-dimensional space and simultaneously moving across the shell of our surface, but never leaving the shell. We're always, like, even as we move through the XY space, we're always still touching the shell of the surface. And so we're basically just reading the pixel intensity at each XY position. Now, I mentioned earlier the word discrete. Basically, what that means is that our XY positions are integers. In mathematics, discrete just means that it is a whole object. You cannot subdivide it any further. Whereas, with a continuous space, you can have 1.5 and 1.2. You are subdividing between 1 and 2. In a discrete space, you can only have whole entire integers. So now we can get into mapping our input images into the surfaces. I have right here a simple example of an image that we're going to use throughout the rest of this lecture. It's just a simple 3 pixel by 3 pixel image. It can be interpreted as the sort of blocks that you see on the right, where they occupy discrete positions, and the intensity of each pixel gives us the sort of height of each of these blocks. We can then take this interpretation and we can turn it into our surface, which is essentially like a 3D mesh with vertices. And the positions of the vertices are determined by the integer XY positions of each pixel and the continuous intensity values of the pixel. Just to sort of help illustrate a little bit better, like kind of what the surface looks like, I went ahead and created a shaded version. So you can kind of see how certain areas kind of fold over certain areas are kind of folded, and it creates these slopes, basically. Now, having all of these surfaces is not very helpful if we don't have something that can interact with the surface, which is where the notion of our brush particles come from. These are particles, yes. I'm calling them brushes for reasons that will be made clear soon. Now, these particles, they do have mass, but they don't have any volume. So they don't occupy space, but they are in space, if that makes sense. Furthermore, the fact that these particles have this mass additionally allows us to allows for the existence of fundamental forces that can operate on these particles. And we'll get into what those forces are very soon. The position and velocity of these particles are two-dimensional because these particles exist solely on the topology of the shell. They cannot leave the shell. So as they move through the XY space of the surface, they are always constantly touching that surface. Our position of these particles is discrete. They're integers because the pixel values have to be discrete. However, we can set the velocity to still be continuous. And in fact, it's very helpful to do so, as it helps prevent us from losing information about how the particles are moving through space. Now, before we start a simulation, we have to do two things. We need to first allocate a canvas. A canvas is just a basic, simple NumPy array where we can store the results of our image processing. It is not a surface. I need to reiterate that a canvas is not a surface. It is simply where we save the results of our processing. However, the canvas does need to have the exact same dimensions of the surface so that there can be a one-to-one mapping between the two. Next, we need to instantiate the brush particles that will exist on our surface. Because if we just have a surface floating around, it's very boring. Nothing interesting is going on. There are different strategies for how we can go about instantiating our brushes, but for now, just assume that brushes are placed randomly on the surface, they're given random velocities, and all brushes have a mass of 1. Way I can move this. There we go. Now we can calculate. Now our simulation cycle that we go through whenever we are in the middle of the simulation is we begin by calculating and applying forces, and that in turn modifies the velocity of our brushes. We then, with our velocity from the brushes, update the positions that the brushes occupy on the surface. Next, we apply the brush effects of these particles to the canvas based on where they are on the surface. And then finally, we remove any dead or inactive brushes that aren't contributing to the simulation anymore. And then the cycle repeats. So to start, we will calculate and apply our forces. There are sort of 4 fundamental forces that are modeled within our simulation. They include gravity, which helps direct particles towards lower areas of the surface. There is a normal force, which can direct and modify the way that gravity pushes things. This is based on the topology of the surface at the brush's current position. We also have momentum, which is just a fancy way of saying velocity with mass. The existence of mass on our particles it influences or sort of tempers how outside forces cause the particle to accelerate. And this very much mimics the Newtonian concept of momentum. And lastly, there is drag, which just reduces the velocity of every brush by a fixed amount every time. It's nothing too complex. It's just a simple multiplying it by some number that's less than 1 but greater than 0. Now this force diagram right here kind of helps illustrate what's going on. It's not 100% accurate, but it does give a pretty good idea of the mathematics that is occurring here. So you can see that that pinkish vector shows us the gravity pointing straight down. The normal force is the green vector, which is perpendicular to the surface. The drag, which is the blue vector, is going in the opposite direction of where the ball is currently moving to. And then the yellow vector, which is pointing the ball downwards, is the resulting acceleration based on the interaction between the gravity and the normal force. Now, as you may notice, between the surface on the left versus the surface on the right, one is steeper than the other, whereas the other one is like a slow, gradual slope. And you'll also notice that this results in the normal force having a different orientation. And it's this different orientation that causes a really interesting interaction with the gravitational force, because the normal force essentially is pushing back or opposing the gravitational force. And as such, when we have surfaces like the image on the left, where it's very steep, much less of the normal force is opposing gravity, because it's pointed more towards the right as opposing up. But if you look at the image on the right, the normal force is pointing a little, like, much more upwards than the other one was, and hence much more of its magnitude goes towards opposing gravity. So what this results in is that sharp drops induce a normal force that is less opposed to gravity, and thus a faster acceleration occurs. Whereas the opposite occurs with gradual slopes, as they have a slower acceleration. And just to reiterate the point about how normal forces are perpendicular to a surface, I included these these diagrams. And they're called normal forces because they are normal to a surface. Normal is just a fancy math word for saying perpendicular. So the next step in our simulation cycle is we need to update the positions of the brushes. So it's each step in the cycle is not really akin to time. It doesn't really correspond to time that well. It's a better way to think about it is each step in the cycle corresponds to one unit of movement. So during each simulation cycle, a particle can move at most 1 pixel, and it has to be moving to an adjacent pixel to itself. So even if it has a very high velocity, it still won't jump all the way across the image. And then this restriction was placed to help prevent any sort of tearing, so that we have one long continuous path of the particles. What the velocity does do is it helps with the momentum calculations of the particle, so it helps it oppose normal forces, as well as the direction of the velocity tells us which pixel that the particle or the brush will move into in the next cycle. So if the velocity is pointing a little more towards the upwards pixel, then the next cycle the particle will move up. But if the velocity is pointed more in a diagonal sense, then the particle will move to a diagonal pixel. Next, we will apply our particle or our brush effects to the canvas. Basically, because the surface and the canvas have the exact same dimensions, a particle's position on the surface corresponds directly to a position on the canvas. And as such, during this step of the cycle, we can apply some sort of visual effect onto the canvas. There are many different ways you could go about doing this. You could even apply really complicated, Photoshop type brushes if you wanted. For me, just to keep things simple, I just have it color the current pixel black. But as I said, there are different. You can really do anything you want with it. Just for now, we're just during this step, it colors the current position, the pixel at its current position, black on the canvas. Now, normally, when a brush's velocity becomes 0, either due to drag or interactions with the normal force, what the algorithm does is it looks for adjacent neighbors which have a lower elevation than the particle's current position. And of those, it picks the one with the lowest elevation, and it sort of nudges the particle a little bit towards that direction, so that it can we can keep the simulation going, basically. And we can explore more of the image. However, a brush can lose all of its velocity and be at the lowest possible point of any of its surrounding neighbors. It may not be at the lowest point in the entire image, but it can be at the lowest point of all the neighbors who surround it. At that point, the brush is effectively useless. It's declared dead by the algorithm. Now, dead brushes it doesn't make any sense to keep them in the update cycle, They just are taking up space and computing time at that point. So we remove them as it helps speed things along as the simulation progresses. Now, all of these physics rules we've defined and the various steps of the simulation cycle, they result in some interesting emergent behaviors. I'll just be going over 3 for the moment, but I'm sure if we really thought about it, we could probably come up with a few more. So first and foremost, the normal forces naturally will push particles away from light regions and towards dark regions. As you can see in the diagram at the bottom left, the green arrows are showing sort of like the direction that the normal force might push a particle if it is approaching that pixel from some angle. Next, the momentum of our particles might allow them to overcome the normal force. And thus, you can kind of think of it as a ball rolling down a hill into a valley, but because it has so much momentum behind it, it's able to roll up the next hill and over the next hill into the next valley. So that's basically what's happening here. And it allows us to travel between dark regions of the image that are otherwise separated by light regions. And finally, statistically speaking, most of the particles will just naturally gravitate towards darker regions, which naturally results in these regions receiving more shading than the lighter regions. And this very closely mimics how an artist draws an image with a pen or a pencil. So, as a part of this emergent behavior, we are essentially, we're moving from lighter portions of the image to darker portions of the image. And these lighter portions have higher pixel intensities, whereas the darker portions have darker pixel intensities. And as such, we can say that we are descending to the dark regions, which therefore makes this a descent procedure. Now, I actually, when I came up with this, I was just having a few beers one night when it popped in my head. I was very much inspired by the underlying mathematics that occur in neural networks, specifically how they operate using something called gradient descent. However, whereas neural networks use the gradient of a continuous mathematical function to determine the direction and the intensity of its descent step, instead, our particles use the normal force while operating in a discrete environment. Hence, why our procedure is called discrete normal descent, as opposed to gradient descent. And you can see on the left some sort of basic diagrams showing on the top how gradient descent works, where you have a smooth, continuous, differentiable function, and we use the gradient, or the derivative of that function, in order to direct like the movement direction, which is the yellow vector. Whereas on the bottom, you can see how all of the forces interact to give us our movement direction in discrete normal descent. Now, we can guide this emergence, because while the current emergent behavior of our system gives really, really interesting results, we can get even more interesting behavior just with a little bit of guidance by modifying various traits of our simulation. We can do things like trying out different instantiation strategies for the brushes, such as playing around with how we give them their mass, or their position, or their velocity. As well as we can play around with the force constants, such as the gravity or the drag, as well as the brush effects that our brushes occur or induce onto the canvas. And we can even have all of these changes that we're making be done dynamically as the simulation progresses. At the very least for now, we're just going to look at some simple brush instantiation strategies, primarily because I promised Jacques that this lecture would not be an hour long like the last one. So, to begin with, we have a simple case study with a test image. I took a picture of a very handsome boy, and I used this picture as our test image for a few different instantiation strategies. So the first strategy is what I call the random field strategy. Basically, all the brushes have a mass of 1. They're placed randomly, and they're given a random velocity. And you can see the result of that in the image on the right, where I just had 1,000 brushes placed randomly and set randomly all throughout the original surface. And then, simply by following those physics rules that we defined earlier, these brushes proceeded to run around and explore the image, and they tracked their paths and basically wrote down their paths on the canvas. And so what you're seeing is the result of those paths that were traced onto the canvas. Now, already, to me, it looks pretty interesting. You can see that it is avoiding light areas, going towards dark areas, and has very clearly mapped out the shape of my face pretty well. Just to drive home this point a little more, I did this exact same case study with a random field, but I did 5,000 brushes instead. And even though there were 5 times as many brushes and the image is substantially darker, it still obeyed a lot of those rules that we set up. It avoided the lighter regions, which you can see were on my cheeks, my eyelids, my ears, my neck. And it gravitated towards the darker regions, such as my hair, my shirt, and then my eyebrows and the outlines of my shape against the backdrop. However, the issue that I found with this random field approach is that there's too much going on. It looks a little too I don't know, too sloppy in my opinion. So I decided to play around with another idea that I called the deterministic bars approach. Basically, brushes are placed along the edges of the image. The top, the bottom, the left, and the right. They're all kind of split and distributed evenly among each of those edges of the image. Then the brushes are given a velocity which points to their opposite edge. So if a brush is placed at the top, its velocity points it downwards, and if it's placed on the right, its velocity points it leftwards, which causes it to naturally seek out and go towards the center of the image. And already we can see that this has resulted in a substantially different image from the previous one. And it definitely appears that the majority of the brushes got stuck on the outside sort of darker edges of my face. But we can see, though, the effects of momentum, allowing some of these brushes to sort of escape those like darker valleys and make their way towards the lighter interior of my face. They even still outlined my glasses, as well as you can see they outlined the inner part of my ear a little bit, which I thought was a pretty interesting one. And then finally, this was the method that I ended up liking the most. I call it the random circles method. It's very similar to random field, but instead of placing the brushes randomly all throughout the image, we define manually a few circles throughout placed on the image, and the brushes are placed randomly inside of these circles. And then otherwise, it's just like random field. They're given random positions inside of the circles, random and with random velocities, and they have a mass of 1. And here, I placed 900 brushes, which were distributed across 3 circles, and honestly, in my opinion, it gave some of the best results, just because it's able to focus more on areas of the image that we find a little bit more relevant. You may also notice that the lines on this image are a little bit thinner than the previous images. That's because I increased the resolution for fun, but the increase in resolution won't really have any effect on the physics simulation. It'll just make the lines appear a little thinner. So I played around with random circles some more, and this was me placing 3,200 brushes. I think I used 7 or 8 circles in a few points of interest around my face, and it gave this, just in my opinion, absolutely stunning result. Like, from far away, this looks like a sketch drawing. And I'm actually in the process of looking for someone with a laser engraver. And I actually want to have this engraved on some wood so I can give it to my mother as a birthday present. But like overall, that this has definitely been my favorite strategy that I have found thus far for guiding the emergence of these particles. I'm sure we could probably get into some really complicated or very interesting, at the very least, ideas. You could potentially even use like a neural network to do some kind of like semantic segmentation of an image, which could help you like guide on like where you want to place these brush particles a little bit better. But I did not bother doing that. I stopped after random circles. So the conclusion of all of this, Discrete Normal Descent offers us a way to sort of organically explore an image's structure without reverting to more complicated and computationally expensive means of analysis. It's basically we're dropping a particle in some image, and that particle, by obeying these simple physics rules, will explore that image while still following the sort of structure of that image. Now, at the moment, the only applications thus far are artistic, but it is definitely possible that this method could maybe be used in commercial settings for other types of problems. However, before that could happen, I think that this would need to be defined a little bit more mathematically and rigorously, as well as there probably need to be extensions and standardizations made so that it can do much more complicated behavior or much higher level behavior. I was also thinking, though, that it might, just in its current state, it might produce some interesting results in other discrete domains, such as if you're doing some kind of semantic search or network analysis, the only requirement being that you would need some way to measure the quote-unquote normal force in those domains. You could probably do it in network analysis based on like the network topology and like the network flow and whatnot. So you could probably do something, probably would apply it to network analysis pretty easily. I would be very interested to see someone apply this method to semantic search. That would be that would be pretty cool in my opinion. So if you liked this lecture, you liked this presentation, go ahead and give the Katin Kollective a like on social media. We're on Facebook and Instagram, and you can follow us on YouTube or subscribe to us on YouTube, where I will be posting my recording of this lecture. I will now be opening up to the floor for our question and answer session for people who maybe want to know a little bit more, or maybe they want something clarified.